Hello everyone and welcome to our Wednesday seminar for a change. And we're delighted to have with us today a very distinguished guest as our speaker, Professor Fabrizio Ruggeri from Italy. Fabrizio is currently the research director at the Italian National Research Council in Milano. He received his PhD in statistics from Duke University and before that his master's in statistics from Carnegie Mellon and his bachelor's in math from University of Milano. He has a very long and illustrious profile with lots of high quality and high volume research activity and lots of awards and distinctions. So I'll try to be brief and summarize some of his major achievements. He's a fellow of the ASA, he's a fellow of the IMS and ISBA, where he's also the first recipient of the Zellner Medal from ISBA. And he's an honorary member of NBIS. I'll try to give the full form.
You're doing very well.
Business and Industrial Statistics. He has also served as the past president of ISBA, of NBIS and ISBIS, International Society for Business and Industrial Statistics. And he's incoming president-elect for the International Statistical Institute, where he was also the past vice president. And he has also served on the editorial boards of various journals. His research interests are varied, but mainly centered around adversarial risk analysis, Bayesian statistics, sensitivity and robustness of Bayesian methods, gamma minimax theory, wavelets, Bayesian non-parametrics, and the list goes on. And needless to say that he has done lots of high quality work in all these areas over all these years, leading to lots and lots of publications and also lots of books. And today he's going to tell us about some of his current and recent work in the area of adversarial risk analysis. So please join me in welcoming Fabrizio.
Thanks a lot. Thanks a lot. It's a great pleasure for me to be at Texas AM. It's a place I've heard a lot. I think my first paper was submitted to a journal with an editor-in-chief of this university. It was Communication in Statistics, Theory and Methods. I think it was Owen or something like that for this university. But that was 30 plus 35 years ago. So that's why I have all this such a long curriculum, because I am quite old, but that's another issue. So what I'm going to talk today is about the recent work, quite recent work I've been doing with some people, mostly in Spain, but also in Washington. And it's about adversarial risk analysis. But before I was told to do some advertisement about some activities. Next year, we will have in May in Madrid, back-to-back two conferences, which I'm very involved. Bayesian inference in stochastic processes, which has been number 13. Someone was involved, was already part of this. I don't know where is the guy. And there. And then there is back to that games and decisions and risk reliability, two conferences which are involved. And then in July, we have the ISI World Congress of Statistics in Ottawa, in which I will become president-elect of ISI. So this is, I'm working for the Institute of Applied Mathematics and Information Technology at the Italian National Research Council. In Italy, we have, like other countries in Europe, we have this academic system in which we have people working in universities, so teaching, and people are just doing research. I am in the second position. That's why I did a lot of work, because I had minor teaching duties. I taught a lot, but not regularly. Sorry, I knew that this was going to happen in this way. So I am there in Milan. And the talk today is about a few words on adversarial risk analysis and about also batch acceptance and acceptance sampling. If you want to know about them, invite me another time. I will give you this older talk, but I'm going to concentrate today especially about two stuff. One is Bayesian approaches to protecting classifiers from attacks. So a few words on classification, adversarial hypothesis testing, binary adversarial classification. This proposal we have done with my colleagues in Spain about adversarial risk analysis approach to classification, and then also the newest one, which is related somehow to approximate Bayesian computation. Despite here there are a lot of items, and the last one there is only one item, adversarial software testing. I'm going to speak mostly about this one, which is a paper that we submitted 4 days ago with my co-author. So it's really new stuff that we've been doing. So I speak most about this one. So my background is essentially in Bayesian analysis and Bayesian decision analysis. So just one slide to remind you about the Bayesian decision analysis. And we have this supports the decision maker in making decisions under uncertainty. So we have a set of alternatives or actions in A, and then there is a parameter theta which depends on state of nature. As a consequence of an action, when theta occurs, we have a C of A of theta. There is also a utility function, U C of A of theta. A major difference between decision analyst and statistician is that decision analysts like utilities, statistician like losses, but is essentially is the same. Then there is a posterior distribution on the parameter after observing some data. And then there is a principle, which is the maximum subjective expected utility principle, which is try to find the action which maximizes the expected posterior utility, which is this formula. This is just essentially one agent, one person against nature. But then the idea in adversarial risk analysis, and I will give the references for key references to this at the end, but it's a work by David Rios Insua in Madrid at ICMAT, equivalent of my institution, but in Spain, Jesus Rios Aliaga at IBM here in the United States, and David Banks currently at Duke University. They have a book and also a JASA paper, which are telling a lot about this. So they are the ones which essentially started these areas of research. Many other people are working on adversarial risk and so on, but the area in which I am in is essentially started by the three of them. And I'm working with David Rios Insua, by the way. So we have, in this case, we have more agents. One is called defender and one is called attacker, and all of them are expected utility maximizers. For example, one of the problems we tackled a long time ago, but in a different way, was competitors in auction bidding for projects. So there are, for example, an Italian company, in that case, we were interested in an Italian company trying to build oil plants in some places in the world, competing with Chinese and Japanese ones. And we were on the side of the Italian company, but it was before adversarial risk analysis. And then a terrorist on the other side, there are intelligence agencies like CIA or our Italian or what else. And then there are also competing interest groups, jobs versus health in risky situation. For example, we have a city in Italy called Taranto, in which most of the people are working for the steel factory. So they are getting the salary out of the steel factory, but also they are getting cancer out of the steel factory. And the problem is what to do with this steel factory. And it's been a big problem. So there are competing interest groups. And also there are decisions by an agent are affecting the others. The point, I'm not a game theorist, but the criticism, at least one weak point of the game theory, is that you are assuming that everyone knows what the other thinks, what are the utilities, the preferences of the other person. And this is not actually very realistic in this case. And this is where the adversarial risk analysis is making a difference. So there is one defender, which is the one we are supporting, which is trying to understand what the attacker is doing. So we are guessing about that and trying to make the best decision for the defender, knowing that the attacker is trying to do the best decision for him. So this is essentially what they are going to do. So this is the work you can find in this paper in decision analysis, and I'm not going to tell much. This is a batch acceptance model. So there is a batch which can be accepted or not by a person. So this could be, for example, something related to screening containers in international port, accepting batches of electronic message of emails or packages of some perishable products. And here in this paper, so we have considered different scenarios in which we have, for example, a loss depending. So if there is just one item is faulty, so this is the case in which we have a batch of M items. If one is faulty, we do not accept this one. We don't want it. So this is one case. The other, it depends on the number of faulty. But how? So if there are M, depends on how many out of M are faulty items. An example could be the adding or changing emails which are spam email, trying to modify them as if they were legit or adding spam email. So we are considering also different scenarios in which the attacker adds some new faulty items, so spam email, or modifies some, in this case, original one, which are spam mails, and then into something which looks legitimate, but that is something, or combining the two of them. So this is, there are a lot of computation, but I'm going to skip it. And then, oh, by the way, spam mail is a problem with Texas A&M, because I've not been in touch with Professor Brani Vidakovich, who co-author of mine for many, many years, a friend of mine for many, many years, because of the anti-spam of this university. Every time I was writing to him, my mail was going not in his spam, not in his folder, but it was canceled, okay, disappeared. Every time he was writing to me, I was replying, but he never got my reply. So for years, we have been in touch because of this. We met at JSM last August. Now that's why I'm here now, okay? And now we have tricked the system, okay? So it's an important problem, the spam. So this is also acceptance samplings in this other paper in IJOR. And here there is a manufacturer which is trying to sell a batch of items to a consumer. See, it stems from a work by Lindley and Simpurvala. Simpurvala has died recently at the age of 81. He was George Washington University. He's been very influential for many aspects in Bayesian statistics, industrial statistics, decision analysis. It's a great loss. And the conference in Madrid, GDRR, is a section devoted there to him about this. So this was, okay, mess, as expected. Okay, now it's going, oh, okay. Perfect. Sorry. I knew that was going to happen. So this manufacturer is doing the following. Is looking at these items, looking at the reliability, for example, of the quality of these items, and deciding if to send this to the consumer, and if, and also how many of them. So there is this problem from the point of view of the manufacturer. And then the idea is that to sell to the customer them. So this is the point. The M phase is to offer a sample and how much it will be. All of them are expected utility maximizers, and we are considered this sort of Bernoulli acceptance sampling problems, in which, as I said, an item could be faulty or not with some probability theta. That's why it's a Bernoulli. And out of that, there are some computations as well. Now we enter more in the interest of what we are doing. Classification. So classification is something which is a supervised learning method in general, and it's applied in many examples, in many cases, computer vision, genomics, and so on. It's an important area of research in statistics and machine learning also. And the point is that most of the people are interested in finding algorithms which are working, which are more accurate, faster, and so on. The interest here is different for an aspect which is not being considered so much, the presence of an adversary which is trying to trick what the defender, just to use the notation I mentioned before. For example, there are tools which are in fraud detection, which are good in finding possible frauds. The point is that the fraudsters are learning out of that. So they are smart and they are changing strategies. So we need to adapt to the behavior of this fraud. So in this case, also there is no common knowledge about what's going on with the fraudster, and so it's again adversarial risk analysis stuff. So this is a work we did about adversarial hypothesis testing. So there are some items coming from a distribution, following some distribution, let's say theta, we will see later, we parameterize by parameter theta. The point is how to choose this parameter theta. One could be good one, on theta denoting good one, another could be denoting something bad. And the point is that there are some data coming from this distribution parameterized with parameter theta, and then there is an attacker which is changing the data, trying to fool the defender. So we will see later on. And let's see immediately, should be here. So for example, the problem should be, we have to decide if a batch of emails have spam or not. And then the attacker is trying to modify something in such a way is going to fool it. And then because there are also some rewards, because if a batch is accepted or not by the defender, there should be a reward for the defender if the items were good, legit, but there is a loss if the item she accepts are spam. And so also there is an interest by the attacker, because, for example, there is an interest in entering in your computer and trying to steal your data by using this kind of messages. Or usually I get messages asking me, telling me that my account is ending in a few weeks, my email account is ending in a few days, I have to do something, or there are 2 million euros waiting for me somewhere in the world, something like that, of course. Something smart. I am aware of societies, companies, which were able to send millions of euros or many thousands of euros to some fraudster by believing in what they got by email. So it's really, it's not just a theoretical problem, it's just a real one. So this is the formulation of this one, and you can see more in this paper in the American Statistician. So we have two simple hypotheses, theta, theta naught, and theta 1. So we have an observation which is generated according to this model depending on theta. It could be, for example, exponential of parameter theta or theta 1. And then there is this, this attacker, which is modifying x by using an action A, so that the defender is observing y. So y is, so the defender has to decide what was the right theta, theta naught or theta 1, knowing that there is an attacker who is a utility maximizer and having some opinions about the behavior of this person. Behavior of this person in terms of the action this person is taking, what this person is thinking of my, as a defender, actions, optimal actions, and so on. So this is something we have to do. So on one side, we are trying to minimize the losses of the, or maximize the utility of the defender. On the other side, there is this attacker who is trying to do the same. So this is what we did. Again, details are here. Now, binary classification, which is somehow related to this one. So now we are entering more in some mathematical details of what we have been doing with my co-authors. So there is a classifier, let's call it C, which receives two types of objects. They could be malicious, so we classify them as y equal to plus, or innocent, y is equal to minus. Could be spam mail or legit mail. That could be a possibility. All of them have some features, X, and the distribution depends on the type Y. Here we have the classification, which has to be done into two separate stages. So we have to make inference from the point of view of the classifier or the probability of Y given X. So we are going to do, so this is what is typically done. So these are the beliefs about the type given the features. And then once we get a new item, we have to decide how to classify it, in which class to put it. So this is the assignment YC, which is based on the previous probability that comes also from training data, and utility related to how much I'm gaining in deciding that it's UC when the true value is Y. And here we have this representation with influence diagram. Essentially, we have the following. So we have Y, which is the one, is the type of the real type of the item we are interested, which is generating this feature X. And now we have to make a decision, which is YC, and then there is a utility related to this one. So this is a typical representation. Square are denoting decisions, circles uncertainty, and double, which are not here, circle are deterministic, and utility are hexagonal. And there are these are conditional relation, and this is information when there is dashed, information which is available at decision time when we have. So this we have to make the decision when X is known. Okay. Plenty of time and plenty of slides. Now, now we have the following. So we have an attacker and a defender. We could have more attacker, more defender, but let's keep simple also because it's already complex, the simple one. So the attacker is going to do the following. X is the true value, are the true features of the item, but the attacker is going to modify them in such a way the defender will make a wrong classification. That's the point. Again, think about the email. There are some features, for example, your bank account data and so on, something which could look like a good, at least I get messages from my bank, in quotes, my bank, with a proper name, everything proper name. But of course, there are something, if you look at the link, we are linking not to my bank, but somewhere else. So there are some features which look like legit. So this is the idea of the attacker, putting them in such a way you believe that it's really a legit message. But so this is the idea of this one. So we have features and they're modifying something such a way you will believe they are good one. So this is the idea. So there is an actual X, but then there is an attack, which is A of X, transforming X into X prime. And now we're making a simplifying assumption, which is the attacker is just modifying items which are malicious. So the one with Y equal to plus. So if there is Y equal to minus, so a legit message, for example, the attacker is doing nothing. This is just simplifying assumption, but you can remove it. And here we have, again, in this influence diagram, and the color are related somehow to the different persons. So here we have the Y, which is the one which is of interest for both the attacker and the defender, or classifier in this case, because there are both colors, and these are leading to X. And then there is this attack, so that the X from the attack leads to X prime. And then here there is this YC, which is affected by this X prime, which is the decision. And all of them are ruled by using the utility function for the attacker and the utility function for the classifier or defender. So this is the representation by using a diagram. Now, the point here is the following. So we have observed X prime, and we have to find the class, the proper class, plus or minus in our problem. And how to do that? Well, we are trying to find the YC, so we have to classify by find the YC, which maximizes what? The expected utility. Here we have different values of Y, which is plus and minus. This is the utility function when Y is the true value, is the value, and YC is what you decide. And this is the probability of C given of Y given X prime. We know this one because I said by training, this is talking about typical stuff in machine learning. So by training, we know the probability of Y given X, so also Y given X prime, which is one possibility. So now we'll do the following. We apply Bayes' theorem, but we remove the denominator, which is P of X prime, because that is equal for everyone, is nothing of interest. So now we have split in two parts, the one in which Y is negative and the one in which is positive. The one in which is negative, I'm just plugging here. So here, instead of PC of Y given X prime, I'm applying Bayes' theorem. So it's the probability of X prime given Y, which is minus in this case, times the probabilities of Y equal to minus. And this is the first part, which is not so relevant. But the relevant part is this one. So this is the case in which Y is positive. But what is this quantity here? The quantity here is somehow related to all the possible X's which are leading to X prime. We, as a defender, are observing X prime. But we know that X prime might not be the true one. It might come from somewhere, something else, which is X. So we have to consider the set of all X such that A of X, so the attack applied to X, leads to X prime. And over that one, we are going to compute the probability of having X prime, you can read it in this way, given that X was the original one, and Y is plus, and the probability of X given the Y is plus. over all the possible X. So here we are doing this one. Expected utility maximization. Here what we have, these are the beliefs about the class distribution, the class which belongs. These are the beliefs about the feature and under no attacks. This is the utility. And this is the beliefs about the action of A, given X and Y. And here is the difference with respect to game theory. We don't know this one. The point is that we don't know what will be the action by the other person, by the attacker. And we have to do something to try to understand this one. This is the critical aspect. So what we are going to do is think about the attacker, the same problem, but from the point of view of the attacker. Again, the attacker has to maximize its expected utility. We'll do the same things. And what is the optimal attack? Well, the optimal attack for the point of view of the attacker, it has to maximize this quantity. What is this one? P is the beliefs. P is the following. So we have PA of C of X prime given X are the beliefs of A about the classification result when C observes X prime. So this is the opinion of the attacker about what the defender will do when she will observe X prime. Can we know that one? No, that will be part of the next step. How can we deal with this one? And then we have here P, which is the probability of the previous one equal to plus given A of X. And this is a quantity, and here we put it here. So this is the expected utility when, so this is the beliefs about C classifying as malicious after observing X prime. So this is the expected utility from this point of view. So when it's malicious and it's classified as malicious with action A, and this is the opposite when it is malicious and is classified as innocent, and this is 1 minus P, and there is some density about P. We take the integral out of this, and this is the formula. I'm not entering too much in details about the formula. So this is the formula. So out of this is possible to get the attacker. The point is that, do we know the utility of this person? No. Do we know this density? No. These beliefs? No. How will we deal with that? Well, we will see pretty soon. So here is the point. Instead of considering, so we have this probability here, we have this probability here, we have this utility. So the idea is to generate probability and utilities from random probabilities and random utilities. And for each one of this generation, we are going to have an optimal values of A star. So this is the idea. So we have random utilities on which we generate, so a class of utilities and a class of probabilities for which we are generating values. And for each one of them, we are solving this problem. We repeat it many times. At the end of the day, we will get a sample about this A star, which are the optimals one. And in the end, we will be able to estimate the probability of what we think is a classifier about the action that the attacker is going to do. It's just the frequency of the number of times in which there is, starting with X, they get X prime. That is, so for each X, so you remember there was the sum over all the possible X leading to X prime. Now we are able to get an estimate of the probability of, once we observe X prime, that is coming from A. And that is what we are getting here. Classes of utilities, classes of primes is somehow related to an area in which I've been working essentially all my scientific life, which is Bayesian robustness. So studying the effect of choosing a class of price of utilities on the quantity of interest, and something somehow related to this one. Now, random utility, what we are going to do, something like this. For example, when it's malicious and this person and the defender is considered it's as malicious, it's a minus a gamma distribution. Why minus? Because we are from a point of view, in this case, of the attacker. So this is the case in which the defender is classified as malicious. What is malicious? So it's a loss for the attacker. His attacks didn't work. So from this point of view, this is the opposite. So this is the case in which it was malicious, but the attacker, the defender, classified it as innocent. Then there is a gain from the point of view of the attacker. So it's positive. And here we are not considering the case in which when it was innocent. So this is just 0. It's a direct. And the gain is just the difference between this quantity and the cost for the attack. So this is the gain for the attacker. We could introduce also some notion about risk proneness, and we have some utility of this form, something like this. Okay, I should go. And for example, now there is an issue about a chain. So I am the defender and trying to understand what is the best for the attacker, who is trying to understand what is the best for me, who is trying to understand what is the best for him, the best, and so on. So we could keep going. We are not going to do that. So there are some people who have been working on that, David Rios and others, but we just look at the first part. How do we put a distribution on, I saw the distribution on the utilities before, now the random distribution on the probability. How do we do that? Well, we are considering a sort of beta distribution. So we are considering a beta distribution where the mean is somehow related to our opinion of the following: the proportion of instances which are originally malicious divided by the total number of divided by 1, if it's proportion. So essentially is this one. So we are trying to use some information about driving this beta distribution, and then we are going to put some distribution of these parameters. So we have a beta with some mean, and then we are considering variance, for example, in a class, or putting doing something random about this beta distribution. The example could be the following, So we have m emails as a bag of words. There are many words in them, and there might be one. So we classify one if a word, for example, bank is there. If it is not, it's 0. And there is a label indicating if the message is spam. So these are the features, the words which are there. And so this is an m-dimensional vector, x1 to xn, and of 0 and 1s. We allow only for one word insertion attacks. It's already complex to do it this way, so we allow this one. We are interested in just one, and here we are interested in 2 sets. What are the the one we are interested? So we are interested in this one, which are the one of the x, so the x, such that they can be okay, all the possible attacks transforming so the indices such that xi is equal to 0. Why is this important? Because these are the ones in which we can make a change going from 0 to 1. So are the indices which are interested in. So there are some words, for example, bank, which is not there. So there is xi equal to 0 corresponding to bank. So this is an index which is important because it could become 1. So we could add the word bank. And this is the opposite. The one, so we have someone which is 1, so there is bank, but it goes back to messages in which the word bank, for example, was not there. So it's one direction and the other. And here we do the following. So we put utilities, random utilities. We put beta distribution with some indices, considering the previous one, but these are just technical details. The major point I show you is already there. And now these are an example we did with well, David Rios has a lot of young people with him who are gurus in terms of simulation, doing machine learning, adversarial machine learning, and so on. So this is most of the work of this one, Roy Naveiro and other co-authors. So we have this data set with there are emails, some of them are spam. There are 54 words. So they're talking about the vectors of dimension 54. What we did was the following. We split the data, 75% for training, 25% for testing. We repeated that 100 times and trying to compare our method with other famous methods called naive Bayes, for it's called. We did that for different kind of utilities, with the simulation of sample size 1000, and we compared the behavior of our ACRA, this is the acronym of our method, and naive Bayes in terms of accuracy, especially, I will show here false positive, but there's also false negative. And what we showed is that our method is more robust with respect to attacks, so is classifying better when data words are attacked. And also it gives a lower false positive rate, so we have less non-spam are rejected as a spam. This is very important, as the example with Professor Vidakovic shows. And so here we have utilities. So the idea is to specify utilities about one is the 0, 1 utility, and I'm going to show you the results for this one. So if you correctly classify is 1 and otherwise 0, or you could penalize if you are correctly, if you are a spam which is classified as legit, or a legit classified as spam. We have 3 different values. So these are the 4 utilities, and then these are the random utilities we have been considering in this case. Opinion of the attacker coming out of this one. This is the random cost. We put also a random risk proneness coefficient. As you can see, all the terms which are all the ingredients are coming from a random distribution. Why are we using this one? Because we don't know exactly what the attacker is going to do, but we have an opinion out of that. And we express the opinion about the behavior of the attacker, about all the parameters, all the ingredients, using classes of distribution. That is the idea. And then for each one, for each simulation, finding the optimal decision for this person, and then considering the sample out of that. So here again, we are going to do data distribution for this one, for different levels of variance. And here is what we get. This in terms of accuracy. This is, sorry. Yes, this is our case. So here you should read it in this way. So there is a maximum value possible for the variance, which is dictated by the fact we want a beta distribution which is concave, yes, this way, because we don't want a convex one, because we don't want probability be to be around 0 and 1 to match. We want concave. So there is a maximum variance, and here we are considering different values of variance, and here you can see from 0, 0 up to the maximum value. Here you can see the behavior of our method with some span over the 100 repetition. This is the plain naive Bayes, and this is the naive Bayes when there are data which are affected by attack, like in our case. So you can see the behavior in terms of accuracy. Ours is definitely better, and also in terms of false positive, positive, you can see here our, which is definitely better than the other one. Here tainted, so I mean with attack or no attack is making no change for the naive Bayes, and this is our, which is better. And of course it's getting worse when we are allowing for larger variance. So we trust, what is the meaning of larger variance? We have an opinion about what the attacker is going to do, but with a larger variance, we are less confident about this opinion. So this is what we are doing. So when we're less confident, we are, of course, losing something, but we're still better than the other one. Now, so we can change a lot of stuff, have more data insertion, but then it become a big problem because of the to the end possible attacks. So there are extensions to binary, from binary classification to multi-label, because there could be malware, Trojan, adware, viruses, and different. Also, we could think about an attacker intervening not only in the testing phase, but also in the training phase. That could be something else. But also attacks on innocent stuff, and now generative classifiers. And this is what is the most recent paper, which is under revision. And here the idea is the following. In this case, we know only, before we are able to know pi of x, here we just know pi of, what is this? Pi of y given x. And here the idea is trying to do something like this. So what is the optimal action in this case? Here again, there is an x, which is changed into x prime. But the point here is also there is this utility, which depends on x. The point is that we don't know this one. We don't know this x. Again, here, I don't want to say much more. Already, I think you got an idea of what's going on. So here we have to do, again, an estimation in the same way we did it before. And we can do that in this way. So now we suppose the following. We suppose that P of x is unknown and P of x prime of x is known. The point is that is the following. We would like to do the following. Let's go back to this one. So here we have we observe x prime, but we have to compute expected utility, sorry, for all the actual x which were modified into x prime, but we don't know that. It would be important to know the probability of x given x prime. Do we know that? No. But what we know is something else, which is we know the following. We know the following. We know the probability of x from training. We know the probability of x prime given x. So going from x to x prime. The point is that we would like to know the opposite. Once we are arrived in x prime, what is the x which we started from? And here we are doing the following. Bayes theorem, probability of x given x prime is proportional to this one. And here we are doing essentially metropolis Hastings. This is in the discrete case. In the non-discrete, in the continuous case, we are going to use approximate Bayesian computation, so that in this case we are generating some new value out of this distribution. Sorry, I don't know how much. Sorry. Okay, I'm making sufficient mess. Okay, sorry. So here the idea is the following. So we have to generate from this one. How we do that one? So we generate from x, from P of x, we generate a value, which call it x tilde. And then how do we accept this value? Well, approximate Bayesian computation allows us to accept a value if the distance of what we are simulating is small with respect to the actual data. If they are close, we accept it. So this is another way of doing it. Now, so this is essentially, we might have problems in terms of computational computation and so on. Also, the attackers could change their behavior over time. So this is something else we could consider. Also, we consider IID sequences, but it could be also autoregressive model. Now, last part of the talk in the last, let's say, 15 minutes, more or less, software. I've been working a lot about software testing. The idea is the following. We have, it's important that once a producer is releasing the software, this is reliable software. The point is that there is a mark. There are other people trying to do the same software, and you have to beat them. And what we are going, there are also some factors affecting this one, which are the number. So the quality of the software is somehow affected by the number of bugs in the software, the skill in detecting bugs. Also, there are other factors, which are when the competitors are releasing, and also what is the interest by the buyers in this case. So there are a lot of costs related to test, to removing bugs before and after the release of the software. Before the release of the software, it costs less than after, because you have to go to the client and intervene with something. Also, there is some reputational aspect. So if you release a software too early, you are beating the others in terms of making the software available earlier. But the point is the quality could be worse, and then you could lose money trying to fix it. If you do that later, it might be obsolete, and then other people would have solved it. So it's important to find the optimal release time. And so there are a lot of people who have been working a lot on software testing. Again, Simple Valley Wilson did this interest book. Other people did a lot of work. I edited this book with Ron Kenneth and Fred Fulton on analytic methods in system software testing. And a paper we wrote for this book is actually the one which motivates what I'm going to present you. Also now we are revising a paper with other co-authors about software testing with possible introduction of bugs. We are not going to consider this aspect, but when you are trying to fix bugs, it's possible to introduce bugs, new bugs. So instead of using what is usually used, which is non-homogeneous Poisson process to describe the discovery of bugs, here it becomes a self-exciting process. Because every time there is a new bug detected, it's possible, Bernoulli random variable, to add or not some extra bugs, and then will affect the intensity function of the process. So the idea here is, this is the paper that we consider a lot. So this is the one we consider this paper, which is the first game theoretic approach looking for optimal release policies through Nash equilibrium. But we moved away from this one, but that was the motivating one. And the idea is the following. There are two producers of a software which has lifetime of capital T, that's the maximum, including testing time, and there is one buyer. This is the simple case, where in the paper we extended to more producer, more buyers, and also there is a probability of accepting by the buyer, which is this one, depending on time, which is this one. For each one of them, it's a function which is at 0 is 0, at the final is 0, because nobody is going to buy your software before you start testing, and also when it's the end of its life. And there's some other properties. So this is some probability of accepting the software if there is no other producer. So this is these are the ingredients. And in this work, there is a cost function, which is important. So this is the cost function when releasing the software at time t, which is made of a cost for the time of test. So this is proportional to the testing time. There is a cost for fixing bugs times the number of bugs you expect up to time t. So this is M of t, which is number of bugs expect up to time of t. And then there is a cost of fixing them after releasing after time t, which is the total number of bugs in the software minus the one you have already fixed at that point. And this one is larger than this one because fixing after the release costs more this one. There are some properties, so they were able to find the optimal release time in this case. But now also there is a sort of expected gain from them, which is essentially, this is the selling price, T1. So let's think of the first producer. This is the selling price. This is the probability of having it accepted by the buyer at time when releasing time X. So this is the expected gain, and this is minus the cost of taking care of the software when released at time X. So this is what happens. And this is the case in which X is releasing, the first one is releasing before the second one. There is the other possibility. The second one is releasing before the first one. And this is the gain. So this is the case. Again, when is possible for this person to gain? Well, this is the price. The probability that the other guy has not sold, the other producer has not sold its software. And then here the probability of selling its own software, and this is the cost. So we have something like this, but of course, here we're assuming knowledge about everyone in this case. What we are going to do is the following. So this is the paper that we have been considering, is essentially similar. Some changes about the acceptance probability, which is for the moment fixed and known, but we will change it. Also, the expected number of events actually is the mean value function of a non-homogeneous Poisson process with some intensity function. But otherwise, it is the same. So here we have the representation of, in terms of diagram. So here we have two decision makers, decision makers, which are the producer, which are affecting the buyer, where their software has some features, for example, number of bugs in them. And then there are some utilities for all them. This is a mistake. This should be Y instead of Z. So here is essentially this one, but from the point of view of our producer, because we are taking it as before, so it's always the same story, essentially. Mathematical details are changing, the environment is changing, but the story is more or less the same. So we are from the point of view of, from the point of view of the producer that we are interested. So we have this situation, so we have decision, the feature of our software, but also there is this uncertainty about what the other producer is doing. So this is the representation in this case. Good. So the cost function is essentially the same. Now, instead of having the mean m of t, now we have a Poisson process instead of that, but essentially is the same as the paper we started from. We assume there were no bugs added during the debugging phase. Also, we assume that the process of arrivals of discovery of faults is the same before and after the release, so, but we could change that. Also, we could have also other, as I said, other producer, other buyers, and so on. But this is just what we are doing. So essentially, here we have to identify what is the random gain for our person. So when X is related to our person, Y to the other, our producer, Y related to the other one. So again, when our producer is releasing before the other one, this is what we get. Essentially, this is the probability of having it accepted. This is the cost. So the gain times the cost minus, times the price minus the cost. And this is what this person is losing, because if it's releasing at time X, the software is not bought by the buyer, then there is a loss. So this is the probability of not having bought it, and this is the cost of testing up to time X, and this is the cost of fixing bugs up to time X. We suppose that if the software is not sold to this buyer, the producer is stopping testing. So this is essentially the idea. So there are two components. The first one is related to the buyer buying it, and this is related to the buyer not buying it. And similar for the other person, it has the other producer, the same formula. But then there is the case in which the other producer is releasing before us, our producer. And again, here we have some possibility. The other producer is selling, and then we stop testing. So we have cost up to that point and no gain. The other producer is not selling, and then our is sold to the buyer. So we have the gain of the price minus the cost. Or the other producer is not selling, and we are not selling, so we have the cost of related of us. And this is translated in this formula. And now we are taking expectations out of that. So now we get this expected utility, which is this one. So the expected utility for X less than Y and for X greater than Y. And then what are we going to do? Well, this is the expected gain. The expected gain is what we computed before, integrated with respect the time in the distribution of the time in which the opponent is releasing its software. So this is what we are interested in right now. So this is what we are gaining when we are releasing at X and the opponent is releasing at Y. The point is that we have to integrate with respect to this distribution. Do we know this distribution? No. This is the tricky part, which goes back under the same tools that we used before. And we have to, because the idea now, if we knew that one, it would be simple. When to release X? Well, the value maximizing this quantity, the expected gain. The point is that we don't know that. How do we get to that one? Well, the mathematical details are here, but here we have to put randomness about the purchase probability of Y software by the buyer, and also our beliefs about Y releasing its product. Again, we are thinking of in terms of the other producer, what it is going to do for its best, so optimal maximization and so on and so on. And then we are going to put some distribution on all the quantities which are involved. Because from the point of view of the other guy, there are all the costs. There is the intensity function of the Poisson process, the probability of acceptance by the buyer, and what that producer is thinking about us, our release time. So we have to put distribution on all of them. They could be Gaussian. You can see here some of them. So, for example, the beliefs, wise beliefs about our release time. How do we do that? Beta distribution, for example, where we rescale the time 0t so that it becomes 0, 1. So this is, we are generating from beta distribution. Again, the trick is always before. We have some quantities we don't know. We are generating from random probabilities, random utilities. And then for each one of them, we are finding the optimal for the opponents. And we compute our optimal. And we keep repeating this one. We do that, or we can do something like this in a paper about perturbation robustness, in which we can perturbate the intensity, the distribution, the CDF. We can perturbate the CDF, it was a beta, by using distortion function. What are distortion functions? Are functions which goes from 0, 1 to 0, 1, such that age of 0 is 0, age of 1 is 1. It's possible to get the new distribution. And an example could be t to the alpha. For example, square root of alpha or alpha to the square. One should be convex, one should be concave. And we are building a class of distribution around this one, and we can generate out of this. And we can do also for all the others. So for all the cost, how do we do that? We generate from the Gaussian distribution centered at our cost. So we have an opinion about the cost, about testing over time, which is C1x, which is our own. We want to know something about C1y for the opponents. Well, we put the Gaussian distribution with mean C1x, our own. And we do that for also for the price and others. The probability, we can transform it to the acceptance probability with some formula. And out of this, what we are going to do, we are generating, for the Poisson process, we can consider different ways. The one I like a lot is my work with former student Cavallo. We are considering a non-homogeneous Poisson process with random intensity function. It's a work by Albert Lowe, and that's it's something that could be done. But these are just mathematical details. You can find them in the paper. If you ask them for me to the slides, I can give them to you. But the key point is there are a lot of quantities which are constant. We generate from a Gaussian distribution centered at value of our own. Our price is the same, centered at our price, the price we are selling, or there is a Poisson process that telling the bugs, the discovery bugs, so we can estimate a Poisson process and then perturbate the parameters. Posterior distribution would be a good idea to perturbate the parameters and generate out of that. But the ones we have these random items, we are generating for them and doing what I told you earlier. So this is just an example. The numbers are not relevant, but what is relevant is the following. Sorry, I'm trying to push the right one. So here you can see there are Gaussian distribution on the cost, Gaussian distribution on the price. This purchase probability is some random. The discovery process is a non-homogeneous Poisson process with some parameter estimated from the data that we consider, and we put some perturbation on them. And also here there is a beta. This is important. The beliefs of Wise over X release time is given by a beta distribution, alpha or alpha. And this is something which is going to change. And this is the random cost function that we saw before. But what is going to happen? So the idea is this one. We would like to do the following. We would like to find the release decision by Wise, and we have to find to maximize the expected gain by this person. So we generate data, the distribution from values from the random distribution, and we get the maximum, the value for this one, the one optimizing this one. So we get a sample of optimizing values, and we get again a CDF, a sample CDF about the optimizing values for Y, for release time. I've used that one for solving our problems, because that was the problem. Finding the distribution of when Y, the opponent, is releasing his software. And this is what we get here out of this empirical distribution. And just to conclude, so we find this one, and then we solve the problem for us. So for example, this is what we get. This is the optimal release time for Y at the very beginning or here, and this is the optimal release time for us in this case. But we can change something. We can think that Y is releasing later on, rather by changing the beta distribution, and we get something like this. So this is this we released earlier. I thought it was. Yes, in fact, it jumped. So it released later. So this is when the opponent is releasing, and this is the optimal time for us to release. So this is probably our release time. And then if you think that it's releasing earlier, so this is when the opponent is going to release, this is the time in which we are going to release. So we have something like this. And just to conclude, well, we can think of some risk averse. We can think of more producers, more decision variables, more buyers. And these are the references. Well, these are the paper, the books, and the paper. So these are the ones you already saw. And these are something on Bayesian robustness and the work on Cavallo, but the relevant work are this one. Thanks a lot. Sorry for taking a little bit.